Okay. Welcome back, everybody. And I hope you had a great weekend. The topic this week is actually a continuation of where we started last week with harmonic oscillations. And we are going to, on Wednesday, I may sneak in some 10, 15 minutes, but not more than that. And then we are going to work on the midterm. And as you know, we have an office hour as well after the regular lecture on Wednesdays. So if you wish to hang around, feel free to do that. And also, we have the same on Friday. We are just going to dedicate Friday on the midterm. Now, I know that some of you may be traveling on Friday, but we will always have this hybrid solution with Zoom. So if that's okay with everybody, we are going to keep this kind of solution for the rest of the semester. And you can always watch the recordings. So very quickly, I wanted to just remind you a little bit of the topic for this week. So we are going to look at damped oscillations, which we started with on Friday. And when we have done damped oscillations, we are going to move over to what's normally called a forced oscillation, right? And with the harmonic oscillator, we can actually solve the equations analytically. So what I would like to start with is more a kind of running the same problem numerically, and then look at the different situations, and then see if we can, from the numerical results, whether we can say something about the way the solutions are going to behave. So let me just remind you of how simply you can actually run a code for harmonic oscillations in one dimension. So I would like to start with the Jupyter notebook immediately. And if we just scroll down in today's or this week's lectures, you will find first all the mathematical exercises, but then we have the numerical solution. And in this case, the numerical solution is actually not very difficult. So we fix the delta t. In this case, I've actually set up I'm going to set up a shorter final time to 20. And I'm going to take away the external force. And if we run the case, what we have now is the damping due to the velocity term and friction. There is the harmonic oscillator term x here. And then we have an external force, which I'm coming back to. But when we run these calculations, depending on this value gamma here, we are going to get solutions like this. And I'm going to shrink it a little bit so everybody sees it properly. So let me try to shrink it a little bit more so it enters the screen. So in this case, we have taken a final time, which runs to 20 in this dimensionless time. And what you see now is that the way it starts will depend on the initial velocity and the initial position. So in this case, I also have an initial velocity, and that's why it goes up a little bit. And then it oscillates weakly. And what we saw last week is that we can actually use some intuition about the mathematical form of a solution. And the mathematical form here, as you can see, you have this kind of oscillating behavior. So that means we could think of a cosine sine envelope, which takes care of the oscillations, but then it's being damped. And when it's damped, then that cries for an exponential decay. So that means that intuitively, by looking at the numerical results, we could say that the solution should be something like a cosine sine times an exponential decay. Then, as we will see analytically today, this parameter, this damping parameter, so this is actually called an undercritical damping. Undercritical because, I mean, the name is obvious because, I mean, the system gets damped in not a critical way. If I put gamma equal to 1, you will see something like this, and then it just drops down to 0. This is a solution which will also depend on exponential decay, but we're going to see today that it contains a little bit more, and depending on the different parameters, it can drop down to 0 faster or slower. But this is also an example of exponential decay, And as we will see, this is called critical damping. And then we have the case when I switch this parameter gamma to something like, let's put it to 1.5, then we are going to get another solution, which is now simply, it looks pretty similar to the previous one, but we're going to see that the mathematical form is just going to be that of an exponential decay. Now, one thing you can do easily here is actually to add an external force, because the only thing you need to do then is to change the acceleration. So what I could do now is to add an external force which oscillates with its own frequency, and then see how the system behaves. And let me see if I can trigger your intuition here. So let's keep this system here. I'm going to change a little bit this gamma so that it has, oh, sorry, I actually did something wrong here. I changed the wrong parameters. This should be 1.5, and then you will see that the damping factor is much more like an exponential. This is a much cleaner exponential. Sorry for that. I was actually changing the wrong parameters. But let me bring this back to 0.5, and I'm going to keep this frequency, and I'm going to have a external force, which you now can see contains a constant, F tilde, and it's multiplied with a cosine, and time times a frequency. And I'm going to let this oscillate a little bit longer. So I'm going to let this oscillate for 200, not seconds, but dimensionless seconds. And it's going to look like this. Okay, what does it mean? Why does it look different in the beginning? So the only thing I've done, I've taken these problems where we have a damping, and then I apply an external force on it. So if you look at the simulations here, and you trust them, what kind of physics would you say takes place here? So if you look at the beginning, the solution is different from what you get when you move on, right? And you see when you move on, it oscillates between -3 something and +3. So it's very periodic. But it's different in the beginning. So any good suggestions? What happens physically? So you have the tools here to run the calculations and then try to do some physics analysis without having done the analytical calculations. I'm going to let you think a little bit. Now let's take perhaps 1 minute and see if you can think what is happening. Why is the solution different when we move on with time from the beginning? Could you say again? Okay.
It's like acceleration.
So you're on the right track, but why does it oscillate in the same way when you move on with time? Say it again. It doesn't need to conserve energy in this case. Yeah. So what happens here is that the external force takes over. And you see in the beginning, the system has a natural frequency and it tries to resist the external force. And then after some time, the external force takes over and the beginning is washed out and it just becomes forgotten, becomes legend, and then legend becomes myth. And I have to do one thing. When I said this, you might expect what is coming now. So when this takes place, so everything which is done in the beginning is lost, this information, and what takes over is the external force, which means that when you are doing this now, and for those of which of you are online, this is what you would see here. Okay. I couldn't resist, actually. This is one of my hang-ups. So what happens here is that this could actually now, when you have this external force which is being applied to the system could just stay on unless you cut off this external force. And then everything from the beginning is just forgotten. Sorry for this, I couldn't resist, actually. Anyway, so you see the numerical simulation is extremely simple. And you can actually then just simply change the force as you want, and you will get different types of behaviors. So what we're going to do the rest of the time today is actually to do this analytically. So we can actually show analytically that we get the kind of solutions we're expecting. The other thing I'd like to say is that if you were to take a pendulum, then you would have something which would be non-linear in x. You would have a sine times x something. And then you cannot find an analytical solution. So the harmonic oscillator case is actually a case where we have analytical solutions. And then we can build up this insight using both the numerics and the analytical calculations. So the rest of the time today, we're just going to go through the analytical derivations, if that's okay. It's not the most exciting thing we're going to do, but it's very useful to have done it. So I'm going to switch back to the whiteboard and try to develop the analytical solution for the problem which we have here. Okay. And let me quickly remind you of what we did on Friday. So we started with a differential equation, which looks like this. So we have the mass, and this is in one dimension. And we have the second derivative. So this is the acceleration. And then we have this term B, which is a constant, which depends on the system we are looking at. And no, not V, but X. So this is the, oops, I'm just pressing the wrong things here. And then we have this term plus Kx. And now we're going to put zero external force. So we don't have an external force applied to the system. And what we did last week was to rewrite the equation slightly. So we introduced this natural frequency, which is the oscillator parameter, or the oscillator strength, or the spring constant, or whatever we call it, K, divided by the mass. We introduced a parameter, gamma, which was then given by this B divided by M times omega 0. So omega 0 is what we call the natural frequency. And natural because it's defined by the constants which define the mass and the spring constant. So it's a system-specific constant. And this is the frequency it will oscillate with if you don't have any damping. So remember that the first case we looked at was a pretty boring one. We had no damping, and then it would just oscillate back and forth with that frequency W0. Now, the case you saw with the applied external force is a system where this external force imposes itself and the system oscillates with the frequency of the applied external force. So that means that this omega, which we're going to see a little bit later, is going to be different from omega 0. In case it's equal to omega 0, we are going to get an interesting physics situation, which is called a resonance. So that means that the external applied force resonates with the system. And that can have dramatic consequences, because then you can get a damping which is not very nice when it resonates with the system. Okay, so these were the parameters which we introduced, and we had a factor of 2 here. This is just historical, why we have this factor of 2. I never remember why, by the way. And then we introduced a dimensionless time, which is now given by this frequency multiplied with time. And then we could rewrite this differential equation as a d of x. This is the acceleration. of this d tau plus this parameter gamma times 2 times d of x, which is the velocity with respect to this dimensionless time. So let's just rewrite it, dimless time. So we will obviously have to scale the equation with the proper time when we now plug in this W0, which is a system-specific constant, plus x, and this is equal to 0. So that's a differential equation which we simulated last time. And the solution to this problem is a solution which now depends on tau. And we saw that we could rewrite this as a cosine. And then we have now, since we have introduced this dimensionless time, so let's just write this in 2 steps. So the solution is actually given by this quantity here, plus a constant b, where these constants a and b are defined by the initial conditions. And this is something which we rewrote as a cosine. And then we have this tau plus b times sine of tau. Now we can rewrite this, and this is going to be useful for the analysis now in terms of exponentials. So we need to go back to the first homework and the first exercise we did, where we looked at the Taylor expansions of cosines and sines, and we found that we could express them in terms of exponentials. So let me quickly remind you of this and how we can rewrite this solution here in terms of exponentials. So let's just do that mathematical exercise first. So what we can have then, if we now go back to what we had in homework number 1, so let me quickly remind you of that. So we have a cosine, and let's just write it like an omega of t. We know that we can rewrite this as a 1/2 of e to the I of omega 0 of t plus e to the minus I omega 0 of t. And then we have the sine of omega 0 of t is something which we can rewrite as 1/2 of I. And then we have an e of omega 0 of t minus e of minus I omega 0 of t. So we can now rewrite the solution which we have in terms of exponentials. And you can easily see that if you plug in the exponential, either e to the minus e omega 0 times t or the other one. So that means that if you plug these solutions in, you will actually see that these are solutions. So if you now look at the original solution we had, it means I can rewrite, and now I'm going to use only tau here. This is something which I can rewrite as a new constant c of e to the I times tau plus a new constant d of e to the minus I times tau. So how can I do that? Now, if you now look closer at what we had, if I look at this constant c and d, and we go back to the equation we have here, this equation, and then we look close at what we have here, these expressions, then we can simply reorder things, and we can rewrite this x of tau as the constant c plus d multiplied with cosine of omega 0. Let's just keep this tau here of tau. So what I'm doing now, I'm simply taking this term here, and it has a factor of c, and I add this term d here, which has now a factor of e to the minus I of tau. And that means that I can rewrite this in terms of a c plus d plus a term I times c minus d multiplied with a sine of tau. And what I have defined here is these constants a and c and d and b, which are now defined as c plus d is equal to the original constant a, and c minus d multiplied with I is equal to this original constant which we have b. So that means that I can now reuse the definitions, and it's easy to see that if I take any of these solutions, either the plus cosine or the negative or the So if I take x of tau here, which is equal to d of e of I of tau, of d tau, then we see that this is equal to minus, and now I have taken away the dependence on this omega 0, which means that what I get then is just e to the minus of e of tau. And the original differential equation, which I had, was actually this one, of d of tau, and this was equal to minus x. So if x now is equal to, so this is actually minus x of tau. And then I can do the same thing with the other exponential, e to the minus I of tau, and you will see that that is also a solution to this differential equation. So this is a typical way by which you would prove that these are differential equations. Now you can actually rewrite these equations in more compact ways, but we are coming back to that a little bit later. So what we want to look at now is the damping case. And there are three damping cases, as we saw. So we are going to introduce three different cases. One is called underdamping. And this corresponds to the case where this parameter gamma is less than 1. And now we are going to see why gamma has to be less than 1. And that's going to correspond to the case where we have a behavior like this one. So we would start with some initial condition, and then it oscillates a little bit, and then slowly it dies out. So this is our x of tau, what we saw in the lecture, when we run the code here. Next, we are going to have another case, which we are going to call critical damping. And in the critical damping case, what we are going to have then is a gamma value, which is equal to 1. So remember now that this gamma is actually equal to b divided by 2 times the mass of the object which we are studying. B is this friction-dependent constant, and then we have this natural frequency omega 0. So the thing we have done now is simply to bake in these constants into the equations in terms of this parameter gamma here. And then in this specific case, what we will note then is something like this. So we have a time dependence, we have x of tau, and then depending again on initial conditions, so this may go quickly down like this. So it gets damped immediately almost. It depends again a little bit on the physical parameters we have, but this is a case where we'll see a sharp damping. And then we have case 3, and we are going to study all these cases. And the last one is called overdamping. And as you will see now, this corresponds to the parameter gamma being larger than 1. And what we will see then is a solution of this type. And I hope I'm going to be able to make the drawing a little bit different from the previous one. So this is going to be more like an exponential decay. So this is a clear exponential decay. And it's going to go like something like e to the minus tau multiplied with some constants. Okay, so what we're going to look at now is the differential equation. So we are going to look at the case with no external force. And the case with no external force, when we now look at this dimensionless differential equation, which we put up. So we have a d of x of d time here, second derivative respect to time, this parameter gamma of d of x of d of tau plus x equal to 0. So this is a differential equation, and it's an equation which is linear in the unknown parameter x. And normally when you have linear equations, so you see x is the unknown quantity. When it's linear, it means it behaves like x here, and then we have the derivatives of x to a given type of derivative, like second and first derivative. So this would typically be called a linear differential equations of the second order type. Now, this is normally a type of equation which we can solve analytically. If you have a nonlinear term, like the mathematical pendulum, you're going to have something like a sine of x. And if you have a nonlinear term, that often means that you cannot find an analytical solution, unfortunately. But let's now look at the general form of the solution here. So what we've said is the following. So a general guess, a general solution, without specifying a parameter which I'm going to call for R here. So a general solution is x of tau. And we found that the exponential is a good solution because we can rewrite sines and cosines in terms of exponentials. And we have not specified this R is not yet specified. So I don't know how much you've been studying differential equations, so you can clearly always go straight ahead and use different mathematical recipes for doing that. But what we are going to do is typically to take a solution form, and then we're going to place it into the equation. And that is going to give us an equation for this parameter R. And that's going to reveal for us the basic mathematical properties of the solution which we have. So we will see that depending on this variable gamma, we can then get overdamping, underdamping, or critical damping. So the typical procedure you will see then, and I hope I've been trying to motivate people for the exponential solution. So when we have the underdamped case, we know that this is a cosine multiplied with an exponential decay. When they have the critical damping and the overdamping, it's an exponential decay. So we can assume that the solution runs like an exponential where we have not specified this parameter R. But we can, by putting the solution into the equation, we can then find an equation for this parameter R. And this is a kind of basic strategy which you often employ in this type of mathematical problems. So let's plug it back into the equation. So we take the derivatives, and if we take the derivative of this solution which we have here, we will obviously get the first derivative here, now the second derivative, and then we have the first derivative and plus x. So if we do that, we are going to get the following. So we will get an A of E multiplied with R of tau. And then we are going to get an R squared because this is a second derivative with respect to tau, right? And then we get the next term, which goes like 2 times gamma. And then I get the R multiplied with A of E to the R of tau, plus this X term, which is simply E to the R of tau. And then we want this to be 0. So this is going to give us an equation if we now assume that E of R of tau is not 0. We're going to get R squared plus 2 gamma of R plus 1 equal to 0. So if A is equal to 0, nothing happens. So that's a solution which is not very interesting. And with E of R of tau is 0, nothing happens. So if we now assume that both A and the exponential are non-zero, then we can proceed and solve these equations here. So if we make that assumption, then we can find the following equation. We have R plus 2 gamma of R plus 1 is equal to 0. And this is an equation we can solve, right? This is just a second order equation with an unknown parameter R. So if we now just look up the definition of that, we know that R is now going to be given by gamma plus minus gamma squared minus 1. Everybody agrees with that? So that means that I can define now an R1, which is equal to minus gamma plus this term, which goes like gamma squared plus 1. And I can define a new parameter, R2 here, which is the same as minus gamma minus gamma squared plus 1. Sorry, minus, it should be minus 1. Sorry for that. it should be minus here. Gamma squared minus 1, gamma squared minus 1. And that means that my solution now is going to be given by these two terms. So there will be a constant A1, which we can use the initial conditions to define, an E of R1 of tau, plus a new constant A2, which is also defined by the initial conditions of R2 times this parameter tau here. And if we now rewrite it in terms of what we have, we can now rewrite it in terms of an A1, and then I have an E to the minus gamma, and gamma is a positive constant times tau, and then I have plus tau times this term gamma 0, gamma squared minus 1, and plus A2 of E to the minus gamma of tau, and then there is a minus tau of gamma squared minus 1. And if you now look closer, so gamma is a parameter which is larger than 0, and it's a real parameter. So this is the term, if you now mark them here, this term here, and this term here, that gives the exponential decay. Give these two terms, they give the exponential decay. So by solving this analytically, we can now see the kind of mathematical behavior which we could have inferred when we run the numerics and we looked at the graph. So we had this case, depending on this value of gamma, where we could have an exponential decay plus something which oscillates like a cosine and sine. So if I now would like to have a cosine sine term, which comes in addition to the exponential decays here, what kind of value should gamma take? Should it be less than 1? Gamma squared, actually, yeah? Should it be less than 1? Could it be 1? Or could it be larger than 1? So what happens if gamma squared is equal to 1? We see that immediately. Then that term is 0, right? And then we have just an exponential decay. This is a case which is going to give us the critical damping. If gamma squared is larger than 1, do we need to worry then? What happens then? What happens if gamma squared is larger than 1 in the square root there? Is that a real or imaginary number? That's real. So that means that the only thing we get then is actually gamma squared. So this is this gamma squared minus 1, the square root, is just going to give us a new constant. And then what we will see then is that there will be two terms. One which goes like gamma times tau plus tau times something. And then there is minus gamma tau minus tau times something. And one of these is going to go faster to 0 than the other one. And that will be the term which will drive things to 0 in a fast way. What happens if gamma squared is less than 1? Do we need to worry? Or do we need to rethink a little bit? Any good suggestions? It becomes imaginary. And if gamma squared is less than 1, so you see the analysis here by just simplifying the equation, getting rid of all the physical constants, and just having this dimensionless equation in time, it means that if gamma squared now is less than 1, this means that this becomes an imaginary number, and that gives rise to the cosine sine oscillations. So you see very clearly now you have the exponential decay times an envelope which will oscillate till it comes to rest. So let's just do that and just look at the solutions which we get. So if we now, when we look at the different cases, what we are going to do now is simply to go back to what we call the underdamping case. And the underdamping was a case where we have an exponential decay which is modulated by this sine or cosine oscillations. So what we do then is simply that we assume now that gamma is less than 1. And that means that we get a term here, which I'm going to call gamma prime, which is given by the square root of gamma squared minus 1. So that means that my R1 here is now going to be given by minus gamma, the original one, plus I times this gamma prime. And then I have my R2 here, which is minus gamma minus I times gamma prime. So then when I collect everything, I'm going to have a solution which looks like as follows. So I'm going to have an x of tau here, and then I have an A1, and I have the exponential decay. So this is unchanged, but then I have an e to the I of gamma prime of tau. And then I have plus my A2 of e to the gamma of tau multiplied with minus I of, gamma prime times tau. And then I'm going to rewrite these terms in terms of cosines and sines. So if I use the cosines and sine solutions, I get an A1 plus an A2 here, multiplied with e of minus gamma of tau. And then I get a cosine multiplied with a cosine of gamma prime of tau, plus, and then I have my I here, and then I have A minus A2 here, multiplied with e to the minus gamma of tau. And this is then again multiplied with sine of gamma of tau. And there you see the kind of oscillatory behavior. And then I can replace everything in terms of a term, which I call for B1. So this should actually have a term 2 here and 2 here. I refine this one as a term A1 plus A2 divided by 2 here. And then I have a B2, which is just this A divided by I divided by 2. And then I have an A1 minus an A2 here. So then I can rewrite everything in terms of x of tau, which is now equal to a constant B1 of V minus gamma of tau. And then I have a cosine of gamma of tau, and then plus B2 of E of minus gamma of tau times sine of gamma of tau. And this is my oscillatory solution here. So let's just frame it in. So that is my underdamped case, where we now have an exponential decay plus an oscillation due to the cosines and sines. So an exponential decay plus oscillations. Due to sine and cosine. And this is what we saw when we run things numerically. We saw clearly that there was an oscillation and there was a damping. And here we can actually prove it mathematically. So this gives us a lot of insight about the actual solution of the problem. So let's now look at the next case where we can put gamma equal to 1 and see what happens then. And that's going to give us the critical damping case. So the next case now is gamma equal to 1. And this is the case which is normally called critical damping. And the critical damping case means then that this parameter gamma prime is actually equal to gamma squared minus 1, and this is equal to 0. So I would then be tempted to write the solution as x of tau equal to this parameter b1 of e to the minus gamma of tau plus b2 times e to the minus gamma of tau. Does that make sense? Have to be a little bit careful here because you have Just look at the expression here. So remember now that we have a second order differential equation. If you have a second order differential equation, it means that we need two initial conditions to define B1 and B2. We need to define the velocity and we need to define the initial position. So if you look at the equation here, what would you say about the mathematical form of these two equations? So B1 and B2 are just constants. Are they equal or are they different? That's the question, actually. They're equal. So because the constants B1 and B2, since the solution is equal, we can only determine either x or the velocity. So we need actually to change the form of the solution here. And the simplest way we can do that, and which is still a solution, is actually to multiply one of them with tau. And you will see then that this is also a viable solution to the problem. So that means that we cannot have two terms which are the same mathematically, because then we can only define one of them. So what we need to do now is actually to change the solution. So these two solutions are equal. So this one and that one, they are equal, and then we can only define one of them. So what we need to do now is to add another solution, add new solution. And the simplest one we can think of, which still has the damping, is actually a solution of the type. So we put an x prime here, which is given by tau times e to the minus gamma of tau. And you will see that this is also a solution if we now plug it in. So let's try that. So let's assume that this is an additional solution and we just call it for x of tau here, just for simplicity. So I take the derivative of this dx of d tau, which enters the velocity term. So this is simply e to the minus gamma of tau. So I use the chain rule, minus gamma of tau times e to the minus gamma of tau. So that's the first derivative. I can now take the second derivative, and then I can plug everything back into the differential equation. So I get a minus gamma of e to the minus gamma of tau. I get a minus gamma of e to the minus gamma of tau. This is not very exciting, guys. And then plus a gamma squared of tau of e to the minus gamma of tau. And then I put everything back into the differential equation, which has been simplified. So when I scale away all these constants, it makes it easier to actually manipulate the equation. Plus x is equal to 0. And if I do that, I'm going to get the following equation. So I'm just going to give you the final term. I'm not going to put everything together here. I hope you don't get disappointed if I don't give you all the steps. So what you're going to get then is that this, when we plug in x and we plug in this term and this term, this is going to simplify to the following term. So I'm going to have a gamma squared minus 1, and this is multiplied with a minus 1 times tau of e to the minus gamma of tau. And this is again equal to 0. And you see now that what follows from this is that gamma squared has to be equal to 1, which again means that gamma has to be equal to plus minus 1. Now, in our case, gamma is defined as this constant b, which is assumed to be positive. The mass is positive and the frequency is positive. So gamma is normally larger than 0. So it's the solution with the gamma equal to plus 1, which is the one which is acceptable. So you see, if I plug in this equation, this new form, that satisfies the differential equation because the equation is satisfied if gamma is equal to 1, which is what I started with. So that means that I have a solution now, which is going to look like an x of tau, which runs like A of E minus gamma of tau plus a parameter B times tau of E to the minus gamma of tau. And you see that this term, the first term here, this term will dominates when tau is small. When tau is small. But that means that the term which really dominates then is actually this term here, because the other one has this tau, which is multiplied with. So when tau is small, then clearly this term dies out. So when tau is small, it's actually this term which dominates. Then when you increase tau, it's actually the second term which is going to dominate. And that's the one which explains this behavior which you saw. So depending on the value of tau, there will be different terms here which will dominate. But this is what we normally call critical damping. And then the final case, which we have, and that is a little bit easier to set up. So if we take that one, our final case. So we have a final case here, and that is that gamma is larger than 1. So that means that this term gamma prime is going to be larger than 0, because gamma prime is the same as gamma squared minus 1. And then the solution is simply given by an exponential decay. So what we get then is something which looks like x of tau. There's going to be a parameter a1, which is defined by the initial conditions. And then I have an exponential, and then I have a gamma minus gamma squared minus 1 times tau. So everything which you see here is just a constant. So there's a decay term there, and there's a new decay term here. And e to the minus gamma of plus, and then I have a gamma squared minus 1 times tau. So this is actually a plain exponential decay. So if gamma obviously is made large, then the decay is, so we can actually make some simple analysis here, because the long-term motion then, if we have a large tau, that will be typically dominated by the term which you see here. So if we have a over long term, I mean, this is the term which will actually be if gamma is large, then this term here will be the one which dominates. And the typical analysis you can do then, if you look at this minus gamma plus gamma squared minus 1, you can look at the term where gamma is much, much larger than 1. What happens then is that this term here goes to 0. Since then, we can approximate gamma squared minus 1 can be approximated with gamma. And that means that in that specific case, when gamma is very large, then it's the term which has gamma plus this term here. Sorry, minus gamma plus, so it's actually this term, because we have minus gamma here, and then we have minus and minus, so that's plus. So then it's this term which dominates. If we then have, on the other case, if we have a small result for gamma, then clearly the term will have actually gamma still has to be larger than 1. But we can actually, if we take this term minus gamma squared minus 1, that is approximatively equal to minus 2 times gamma. So what I get then is something which runs like this, like A1. So the first term, I have minus gamma plus gamma. And then the next term goes like plus an A2 of E to the minus 2 gamma times tau, when gamma is getting large. But keep in mind that gamma here is always larger than 1. So depending on the value of gamma, like in this case here, if we choose gamma equal to 1, which in turn means that we can have a large resistance or damping term, which could be due to the damping itself, or it could be to a large natural frequency. No, sorry, a small natural frequency or small mass. So these are the kind of mathematical behaviors which we can analyze depending on the values of this parameter gamma. And then we can compare the analytical result with the numerical result. And this is where we're going to stop today. So if somebody wants to hang around, we can discuss the midterm if you prefer that. Or on Wednesday and Friday, we have more time because there's nobody coming here after us. But I don't think there will be anybody today either. So if you wish to hang around a little bit and discuss the midterm, feel free to do that. If not, I'm going to just stop the recording and we see each other on Wednesday.